In the last class, we had found out expression of work done by a constant force. Now let us today find out expression for work done by a variable force. To understand this, let us consider a body is moving along an arbitrary path. Arbitrary path is a path in any direction. So this is an arbitrary path AB by a force which continuously change in magnitude as well as in direction. So this body is moving by a force which continuously changes its force in magnitude and direction. At this point the force is F1. It makes an angle theta 1 with the direction, and F2 here it makes an angle theta 2 with the path, F3 and Fn. So this force is continuously changing its magnitude and direction. Now let the whole path AB be divided into small segments. The small segments are delta S1 here, delta S2, delta S3, and there are many paths, and the last point is say delta Sn. Assuming that these segments are so small that the force practically remains constant at these points. So this path delta S1, delta S2, S3, they are so small that at those points the force practically remains constant. Now if you resolve F1 has two components, F1 cos theta and F1 sin theta. So all the forces have two components, cos component, this is cos component, and this is sine component. So all the forces have cos component and sine component. Now we see that along the direction of motion only the cos component of the force is taken into account. For example, say at this point the force responsible for motion is F1 cos theta. At this point the force responsible for motion is F2 cos theta, and so on. So the last point is Fn cos theta n. Now work done at those points, so let us write it as, in the first point it is say delta W1. Delta means small. Delta W1 is equal to F1 cos theta 1 into delta S1. So this is force into displacement. At this point the work done is W1. Similarly, delta W2 is F2 cos theta 2 into delta S2, and so on, so on. The last point will be delta Wn is equal to Fn cos theta n into delta Sn. So these are the work done at various points. Then the total work done W is given by delta W1 plus delta W2 plus delta W3 plus dot dot dot, and the last point is delta Wn. So let us put down the values now. So the values will be F1 cos theta 1 into delta S1 plus F2 cos theta 2 into delta S2 plus, let us write the last term now. So last term will be Fn cos theta n into delta Sn. So or we can write that W is equal to summation of Fi cos theta I into delta Si. So here I is equal to 1 to I is equal to n. So we can write summation of this quantity. Now if the length of the segment is chosen to be small, that delta Si tends to 0. Delta tends to 0 means that the displacement is close to 0 but not 0. Then we can write W is equal to integration of A to B, then F cos theta into ds. So F cos theta into ds, or we can write W is equal to integration of A to B F bar into delta S bar, because work done is dot product of force and displacement. In this case, F cannot be moved out of the integration. Here this F cannot be moved out of the integration because here F is a variable quantity. If F was constant, we could have taken it outside, but here F is a variable quantity. So if say, let us write case 1. The case 1 is F and delta S are parallel. R parallel means theta equal to 0 degree. So theta equal to 0 degree, W is equal to integration of F ds. If F and ds are anti-parallel, anti-parallel means theta equals to 180 degree, then we can write W equals to minus integration of F ds. And lastly, that this is case 2. This is case 2, and let us say case 3. The case 3 is if F and, so all these are bars, these are all bar, F and ds are all bars. F and ds are mutually perpendicular. Mutually perpendicular means theta equals to 90 degree. Then W is equals to 0. So this is the expression. This is the expression for work done by a variable force. Now let us find graphical interpretation of work. That means we can find out work from a graph. Now if we plot a graph, displacement against force, then we can find out the work done by the body. So work done can be calculated from the force displacement graph. So this is displacement, this is force. The area occupied, these are the areas. The area occupied by the force displacement graph gives the amount of work. Now let us take one example. First one is, remember, it is for constant force. So let us find out work done by constant force. So here force and displacement graph for a constant force, this is a constant force, is shown in the figure. Then let us write the area of the graph. So area of the graph is OA, OABC. OABC is the area of the graph. So we can write it as this, as OA into AB. So OA into AB, how much is OA? OA is your displacement S. And how much is AB? AB is parallel to OC. So this is into F. So this side is F, this side is S. So F into S basically is your work. So if you want to find out work, you just find out the area under the curve. So here this is displacement, this is force. So if you find out just the area, that gives you the amount of work done by a constant force. Now let us find out work done for a variable force. Variable force. So let us see how to find out variable force. Now force displacement graph for a variable force is shown in the figure. Now what we do is, so this is a variable force. The force is changing in magnitude and direction with respect to the displacement. So what we do is, here we draw two vertical lines. The vertical lines are AB and CD. Now this AB and CD are very close to each other. So the area ABCD is equal to AB into BD. AB into BD. This is F into ds. So this side is F and this side is ds. Now the whole displacement is S. This is a small displacement. So this is ds. So this is ds and this is the force. Now force at this point is F. So F into ds is nothing but your dW. So dW is the amount of work done at this small space. Now net work done W, the net work done for the entire space W is given by W is equal to summation of dW. And what is summation of dW? It is summation of area with summation of area A, B, C, D. That's the summation, the whole curve. So W is equal to nothing but area below the curve, or area below the curve OPQ. So the whole curve is OPQ. So W is basically the area below OPQ. Thus, area occupied below the force displacement curve represents the amount of work done. So what we do is, in short, for a variable force, this is the graph, we take a small portion of the graph. For this small portion, we find out the area dW. Then what we do is, we take the summation of entire area. So if the summation of entire area means this is the summation of entire area, gives you the summation of total work. So W is basically the area below OPQ. That's how we find out work done under constant force and variable force by graph or graphical interpretation of work.